In this video, I'll be providing you with an overview to the modeling process. Know what question or questions you're trying to answer. Write the question down. Put it in your pocket. I'm serious. Carry it with you at all times. Don't shake your head in agreement with me. Do it. This is where good models begin, by knowing the question that you're trying to answer with your model. Models are intended to be a representation of reality. They are a simplified and generalized statement of the most important elements of a real-world situation. They are an abstraction to gain clarity. They reduce variety and complexity to a level where we can understand. So, for example, if I was inviting you to my house and I provided you with a map, and the map was real life size, and everything that you pass between your house and my house was drawn to real life scale, that would be ridiculous. It would take the largest piece of paper in the world. I can get you there. We can abstract to gain some clarity. We can drop out a lot of the details. I can tell you, go north to Highway 1, travel for 15 miles, turn left on Highway B, travel for 2 miles, and so on, and get you there. And that's what models do. They get us there. There would be answers to those questions you're carrying around in your pocket. I like this example. Hit the pause and try it out. It's a wire around the Earth. Imagine that we could take a thin wire and wrap it around the Earth from one pole to the other. Now imagine that we stretch that wire out flat and add 10 feet of wire to it. If we were to take the wire and rewrap the Earth with it from pole to pole, would there be any space between the Earth and the wire? Could you stick a knife between the Earth and the wire? Could you crawl underneath that wire? Could you walk under it? Could you drive a truck under it? This is a silly problem, but it's easy to imagine, and it's very hard to solve without some abstraction in math. So it's a good illustration of how models help us answer questions that sometimes can be answered in no other ways. Here's how we solve that problem. The circumference of a sphere is given by pi times its diameter, and the diameter is 2 times the radius. Now I've decided that I can solve this problem by figuring out how much 10 additional feet of circumference adds to the radius. I don't even have to know the Earth's radius. So we'll build the simplest model that we can. Here you see the value for pi, 3.142, and the circumference is 10 feet. There's an equation there. 10 equals pi times 2 times the radius. And we're going to solve it for r. So you see the arithmetic there that does so, and when we solve for r, we find out that the radius has increased by 1.59 feet, or about 19 inches. And I could easily crawl under the wire. So we've used a mathematical model to solve a problem we couldn't have otherwise solved. And that comes up in risk assessment all the time. You've already encountered many different models that look quite different from our wrap a wire around the Earth model. Vibrio parahemolyticus in oysters has been one of our case studies, and we ask, how many people get sick from Vibrio parahemolyticus in oysters? What's the probability of getting sick from eating a raw oyster? How effective would refrigeration within 60 minutes of harvest be in reducing illness from Vibrio parahemolyticus in oysters? What's the risk of eating raw oysters to people with liver disease? There are so many questions that we can pose, and each one will require a model designed specifically to answer those questions. Let's talk about building risk assessment models and following the steps that you found in your textbook. So this is just a brief review. Please feel free to ask questions if you have questions about any of these steps. We begin by determining the objectives of the analysis. What questions are you trying to answer? The remaining steps in the model building process are all meaningless if you do not know the objectives of your analysis. Once you have those objectives firmly in hand, you build a conceptual model. Identify the state variables. Talk about how they are related. Let's have a look at a couple examples. Here's a conceptual risk model for getting eggs from the farm to the consumer, and even beyond, because what we're interested in here are public health outcomes. Here's another conceptual model. This one describes how pests present in Mexican avocados could cause an outbreak of those pests in the United States. Once you have a conceptual model you're comfortable with, it's time to convert it into a specification model. We do that by developing relationships among the variables, specifying equations, and other kinds of logic and other algorithms that are needed to solve the problem that you're addressing. Then you need to turn your specification model into a computational model. This would require collecting data or inventing some test case data and building a computer program or some other kind of tool that will be used to actually make computations. Once the model's built, you verify the model. Is it consistent with the specification model? Did you get the relationships among the variables correct? Are the equations properly specified? Does the computer model represent those equations accurately? Is the program correct? This is the time to debug, review, and test the model. Once you've verified that the model is, in fact, an accurate representation of the specification model, now it's time to validate the model. Here we want to know, is the model consistent with the system that we're analyzing? Data validity is desired when it's possible. That basically would mean you would use some of your data to build the model, holding back some other data. So once the model is built, you would take the data that you held back, and see if the model faithfully reproduced it. But that's hard to do with risk assessment because very often we're dealing with uncertainties and a lack of data. So if you can't use data validity, have an expert compare the system data to the model output. If they can't distinguish one from the other, then we say the model has face validity. Once your model is verified and validated, it's time to design simulation experiments. What parameter values will you use? What inputs will you vary? Think about those experiments that you're going to have to do to answer the questions that you're carrying around in your pocket. Once you've designed the simulation experiments, it's time to make production runs. Be systematic here. Record your initial conditions, the input parameters, the outputs. Look at baseline and mitigation conditions, the with and without conditions that you've read about, because there is a sequence that you can run your simulation experiments in that will minimize your time. So be systematic in discovering that sequence before you begin the runs. Once you've made the production runs, it's time to analyze the simulation results. This task is statistical in nature. After you've done your statistical analysis, it's time to organize and present the results of all that analysis. You want to get information from the data to the decision makers in a useful form that will support their decision making. One of the things that you want to be sure that you do in this process is answer the questions that you're carrying around in your pocket. After you've done so, now it's time to document the model and the results. You would summarize insights gained, offer specific observations and conjectures at this point in the process. There are times in risk assessment when you are required to model some sort of system. Here's just a little bit of the language that we use in talking about system models. It can be a deterministic model or a stochastic model. That deterministic model can be static or dynamic, and dynamic models can be continuous or discrete. Let's define these terms now. A deterministic model has no probabilistic components. In a static model, time is not a significant variable. We are looking at a system at a point in time. When you're looking at a dynamic system, you can do it in a continuous way, and in that case the variables are evolving continuously. This often requires the use of differential equations. A dynamic model that is discrete relies on a piecewise constant function of time. So, for example, we might look at the model every 30 minutes to see what's happening, or once a year, depending on the problem and the system that you're analyzing. We can divide models into two broad types, physical models and abstract models. Physical models are usually iconic models or analog models. An iconic model is a scaled-down replica of the object, system, or process under study. I live in Maryland, and we have the Chesapeake Bay here in my state. And on the eastern shore of my state, there was a 1-acre shed, and inside the shed was a 1-acre scale model of the Chesapeake Bay. So it was built to replicate the bay. If you grew up building toy models, planes or cars or those sorts of things, these are also iconic models. This is different from an analog model. They look like the reality that they represent, and a flight simulator is the best example of an analog model. Abstract models deal with real situations using symbols rather than physical devices. So we rely on theories. And the majority of our abstract models are mathematical models, and they use the mathematical symbols that are well known to all of us. But let's begin with descriptive models. They represent an existing situation, and the symbols that they use to represent it are words. We provide a mental image that's translated into a verbal description, and then we might write that down. Or we might develop an abstract model from it eventually. Descriptive models can be helpful in revealing the structures of problems. Mathematical models go further than the descriptive models. They provide logical and quantitative relationships. There are lots of models we use for programming: linear programming, integer programming, nonlinear programming, equation systems. All of these are good examples of mathematical models. We can identify another category of models, simulation models, and here physical models re-enter. We mentioned the flight simulator just a moment ago. Simulation models can also be mathematical, and they can rely on numerical processes like the Monte Carlo process that we've become familiar with in this class. Simulation models come up an awful lot in risk assessment. Simulation is a legitimate technique for solving problems when analytical solutions aren't possible. Analytical models represent reality. Simulations imitate reality in a simplified manner. And that's the major difference between the two. There are some real advantages to simulation models. They allow for controlled experimentation. We can look and see how different regulations on oyster harvest will affect the number of people who get sick from Vibrio parahemolyticus in oysters. They sometimes reveal new facts about a problem. As we build simulations, we understand the problem better. We can use a patchwork approach to model building when we're doing simulations. We can build a part of a model that would simulate the probability of an aquatic nuisance species entering a new watershed, and that can be separate from the consequence part of the model. I'm hoping that you find that simulation models can be an effective training tool. They have a broad range of applications. Anything that you can do with a spreadsheet, any kind of computational model at all where you have some uncertainty, can be replicated with the simulation model. Models that are costly or time-consuming do sometimes result. So this would be a disadvantage of a simulation model. Sometimes powerful computers may be needed. Hopefully that won't happen in any of the risk assessments that you're doing. Improvements in desktop computational ability have pretty much eliminated this problem for all but the largest problems that people are doing in risk assessment. These simulations are very sensitive to how you formulate your model, so that if there are different ways to do that, you might find those different ways yield different answers. Because it is a simulation and an imitation of reality, there is no guarantee that you will ever reach an optimal solution. The user-friendliness of the tools like at-risk and others sometimes encourage us to overlook analytical techniques and better solutions to our problems. It's so easy to turn on your computer, open up a spreadsheet, and open up at-risk and start building a simulation that sometimes there are better solutions and we don't think about them. So here are a couple rules of thumb I'll offer you. Calculate first and simulate second. If you have a problem that has an analytical solution, calculate the answer. Don't simulate it if you possibly can. Second, if you're going to build a model, keep that model as simple as possible, but don't make it any simpler. And third, every iteration of a simulation model should be possible in reality. In this course and in this program, we focus on spreadsheet models because that is a technology that's available to just about everyone. So when we talk about building computational models in spreadsheets, clearly there are concerns about determining the model's structure, the calculations that you're going to do, equations that you will develop, probabilistic scenario analyses, the systems that will be involved, the processes within those systems. All of these things have to be determined, and their structure needs to be specified as well. You have to quantify the variables and the relationships among them. One of the issues you will always encounter in doing this is trying to figure out what is the appropriate level of detail or the level of resolution of your model. Do you want a realistic model or a useful model? A realistic model would have all of the aspects of a problem in it. A useful model gets you to answers with as few details as possible. So if we disaggregate a problem, your models get bigger. If we use abstract models, your models get smaller. Let's stick with this idea for a moment because it's an important one. If you are disaggregating a problem, your model is getting bigger. The reason to disaggregate a problem is to get to a tangible level. Problems can be very abstract, and if you break them down and get to levels that people can understand, that can be helpful. Nuclear power generators breaking down is a rather abstract idea, but when we get it down to the level of a switch fails or someone falls asleep, that's very tangible. So this is a level that's easy for us to envision. Once you get it disaggregated, very often what you'll find is that no one part is too critical. Aggregating the results in the output can be more accurate than direct estimation. So we take those results from those little pieces and aggregate them up, and that is sometimes more accurate. But such a model requires a great deal of data. The alternative is to use a higher order model. This requires more abstraction, and we do that when details are not possible or practical to get. We also do that when we can get an answer with an abstract model. This is important for those who work without data to understand. In developing nations, databases are not quite as rich. Abstract models are more common there. You have to be able to identify the key elements of the system or the process that you're modeling, however. So this means trade-offs are going to be important. What you give up and what that costs you. In spreadsheets, we've talked about using rapid iteration prototyping. The people who built Word, the word processing program, Microsoft's Word, did not build the software package that we see today. Somebody started originally by saying, wouldn't it be neat if we could type words endlessly. And then somebody said, yes, that would be neat, but wouldn't it be neater if that fit on a page? So they put in a line break. And so gradually they thought of all the little features and gradually built the software package that we have today. You do the same thing with your model. Build the simplest model that you can. Power it up with some test case data. Just make up some numbers that are plausible. And see if that model can answer the questions you're carrying around in your pocket. If the answer is yes, then stop, go get real data, you're done. If the answer is no, then revise the model and repeat the process. Model building could easily be the subject of many semesters of study on its own, and modeling dependencies would be an important part of those semesters. Models should prevent production of any unrealistic scenarios. When you build a model and you hit F9, whatever shows up in that model of yours ought to be able to show up in reality. We do a lot of linear work in our model building, but remember, not all relationships are linear. So when you have nonlinear relationships in reality, you need to use nonlinear relationships in your model. You need to recognize interdependencies among variables and model them. Things that always happen together in the world must always happen together in your model. Things that can never happen together should never happen together in your model. Things that move in the same direction, things that move in the opposite directions, these should move those ways in your models. So paying attention to correlations, equations, and linkages becomes very important to make sure that you have captured dependencies appropriately. Building your computational model is very much like putting a puzzle together. But once you've done all that, put your model together and run it, let me offer you two cardinal rules for documentation. Number one, first and foremost, help people to understand your model. Help them to understand how it works, how you put it together. Second, make sure you are the first person to point out the weaknesses of your model. Do not hide them from others, especially in risk assessment that is intended to support decision making. Even though spreadsheets are important, you've got to give careful thought to how you lay out your model. One way to begin is with a good descriptive title for your model. That's a lot more important than you might imagine. Then the first obvious thing is to have a separate input data section. Have a separate page where all the inputs get listed. Make sure if you're using inputs and outputs and intermediate calculations that you use a consistent color code. Once you put all the input data into one page, then when you build your model, you would reference inputs only with a cell reference or a range name. You would not use actual data values or parameter values in the model itself. Always refer to the value on that input data section. So it's important that you format your cells appropriately. If you have a separate section for input data, make sure you have a separate page for output data. This is where you would collect all of those outputs from your model that are going to be important to answer those questions you're carrying around in your pocket. If you have a separate input and output section in your model, then it stands to reason that most of your model is going to be a separate workspace. This is going to vary depending on the problems you're dealing with. You may have exposure assessments that you're talking about, or perhaps a dose response curve that you're developing. You may be dealing with a production process or some other sort of processing. So make sure that you have the ability to break complex calculations down into several cells to minimize errors. As a matter of fact, if you have a complicated model, break the model down into several separate work pages. A separate page for exposure, a separate page for dose response. Perhaps you will have a separate page for risk characterization as well, which will feed back to your output page. Break your model down. The tabs at the bottom of your model are free. You can have as many of them as you like. Label them carefully and keep your model carefully laid out and constructed. Do not wait till the end to try to explain and document your model. Document things as you go. Jot down assumptions. Write down notes on structure. Put comments in comment boxes next to cells so that people can understand where this value comes from, what that value represents, or perhaps how you derive the equation. If you got something from a journal article or from some other place, you can put sources next to cells in your model. Formula tables, I'll show you an example in a moment, can also be helpful. Use colors to work for you. If I tell you that inputs are blue, outputs are red, and intermediate calculations are green, then as soon as you look at a spreadsheet, you are immediately beginning to get some information about how the spreadsheet is structured, how it is built. In this slide, you get an idea how formula tables can be helpful. At the top, you see blue inputs, red outputs, and below that you see another iteration, so the numbers are different, but you see the blue inputs, the red outputs, and immediately below that is the model structure. Animals imported is cell B1, disease prevalence is cell B2, disease positive animals is cell B3, and to the right you see the actual formulas written out. This might not be practical with a very large model, but for small and moderate sized models, displaying the formulas below or next to the cells can be extremely helpful to others who are trying to understand your model. Spreadsheet software has been made user-friendly, so use the spreadsheet's number formatting, round things off, control the number of digits, vary the fonts, the size, the use of bold and underline for emphasis. We've talked about how colors can be important. There are other aesthetic features that can help as well. Borders and grid lines turned on and off, protecting cells, changing alignment, offering comments, and all those sorts of things can help you organize and emphasize your model's structure. And a final note, try to minimize non-data ink in the graphics that you produce. Turn off grid lines, avoid fancy borders, don't use shadows or 3 dimensions for 2-dimensional data. Use good titles, label everything, and then document your model. A user's manual is ideal. Good notes, comments in cells, all these things are essential. What we want to do is avoid the bus accident catastrophe. For many years in the U.S. Food and Drug Administration, there was one person who did all of the quantitative risk assessment. And if that person had ever been hit by a bus, the entire agency would have been in trouble because he was the only person who knew how to build and use the models that he had. So we want to avoid this catastrophe. Document your models. Here are a couple of takeaway points. Get the questions right and write them down. Remember, models are simplified representations of reality, so know the model building steps and work through them. Simulation, one type of model, is a numerical technique. Simulation models are either larger, the more realistic they are, or they are higher, meaning the more abstract they are. Model dependencies are often the hardest part of building a model. Rapid iteration prototyping can help you.